Hello again. This will be the last time you'll see me today. Try not to take too much of your time. So, unlike my first talk, this is not related to my work in any way, so it's more of a hobby kind of thing. My wife likes to say that you're hacking on some H again. She doesn't like it. Anyway, so how many of you in this room have ever used Rust? Oh, okay. I really expected zero. How many of you heard about Rust? Oh, all right. It's better than I thought. So I'll spend a bit of the first part of the talk to just skip through what Rust is and why I came up with this. And the second part would be about the HDF5 bindings library for Rust. Okay, so Rust is it's a programming language. It's not really new. It was conceived maybe in 2008 or 2009 in Mozilla, and so it's a low-level system programming language focused on safety, particularly thread safety, memory safety, and safe concurrency. It's somewhat similar to many languages like C++ or maybe Ada, Haskell, and or Camel, and it's really paranoid about memory safety, which is kind of the core thing. It's performance-wise, it's quite similar to C or C++. In fact, in many cases, it is faster than C, mainly because it uses LLVM as a backend. In fact, Rust contributes a lot to LLVM development in general, which also benefits Julia and all the other series of JIT languages as well. It may be actually faster than C in equivalent scenarios when because Rust knows more about like scopes and variables, so it can provide LLVM with better intermediate representation. So LLVM can then optimize code like a bit more. So a few things. So first, there's no garbage collection at all. So there's no runtime. All of the deallocations are completely deterministic. So when you compile something, Rust already knows when it's going to deallocate and what. There's no reference counting. It's really hard to cause undefined behavior, and if you can do that in safe Rust, then you should probably open a ticket on Rust GitHub. There's an unsafe mode where you can do stuff like raw pointer stuff and etc., which is required to work with CAPI. But you have to do this in unsafe blocks. So in a typical library, you can easily scan for those blocks to see which are the ones that may potentially cause like segfaults and stuff. In normal applications, you would never use unsafe blocks, so you would just use safe Rust. Yeah, so it's impossible to create like dangling pointers, null references, data races between threads and stuff like that. It has unique ownership model and borrow checker. So this is a thing that's quite unique to Rust. Reference safety is verified at compile time. So like GCC or CLang, if you create local variable, then you return a reference to that, they will shout a warning at you saying, oh, okay, this is like a leaking reference, but in Rust it's just not going to compile. And there's lifetime management, which is a specific thing where Rust tracks the ownership of various variables and tries to prove that what you're doing is actually correct. So really quickly, what's the ownership model is. So each variable has an owner. So values have, there's values, there's variables. So each value has a variable that's called the owner. This can only be one. When owner goes out of scope, the value is dead. So basically it's dropped. And the values can be borrowed through, same as in C++, through constant mutable references. And there's two rules, like references may not outlive the owner. So you can't return reference to something local outside. And one of the most important ones is that at any given time, you can either have a single mutable reference or any number of const references, but you can't have both. So you can't have one mutable and one const. reference, send them to different threads and get a data race, for example. Or you can't have two mutable references, send them to threads and cause another data race. It may seem like an overkill initially, but it actually works, and this is exactly what prevents all the like dangling references and data races. Also, unlike C++, everything is moved by default, so it has move semantics. In C++, there's a blog post somewhere where some guy was counting the number of ways you can initialize a variable in C++, and I think it was 52 or 53 if you include initializer list and all the like crazy stuff. In Rust, there's just really only one. A few more things. There's a proper module system with privacy layers, so there's no text includes like in C++. There's no text expansion of macros. Instead of there's hygienic AST macros that by hygienic I mean you can't leak any symbols outside of scopes. There's procedural macros. This is basically Rust that runs at compile time and receives a syntax tree of Rust and emits Rust back. So it gets pretty meta. But it's nice because you're just writing Rust all the way. You can write build scripts that do custom stuff like look for libraries, link things, which is required for HDF5, for example. It's also written in Rust and it's runs at build time. There's a built-in build system. There's package manager with proper dependency resolution and versioning. There's built-in documentation generation, benchmark stuff, and unit test framework. So that all comes with the tooling. Okay. A few more things. So first, there's no OOP in Rust at all. There's no classes. There's just structs. There's no constructors. Instead, there's structs and there's enums. Enums are some types, but they're not like C enums. They're more like Haskell enums or ML or Camel enums. So they're proper sum types, algebraic data types with proper kind of functional language style pattern matching and all of that. So this is just a short example from a piece of the HDF5 crate that deals with filters. So you can have various arms of variants of enums. They can contain more types, which can contain more types, and then you can pattern match on that. Okay, and all matches are exhaustive and things like this. So it really forces you to write correct code in a way. Error handling. There's no exceptions. There's no try catch. Finally, none of that. There's no error code is non-zero, and just check it yourself. And you forgot about it, you get a seg fault. There's non-recoverable errors, which is basically panic. It unwinds the stacks and quits. You can't catch that, which is something like you run out of drive space or something like this. And there's recoverable errors, which is quite similar to, again, Haskell and OCaml. It's a result type, which is a sum type. So something can be either okay or not. And this is an example from Rust standard library. You just open a file, but you don't get a file object back. You get the results. And you can't use the file unless you do something with it, with the results. You have to match. If it's okay, then you get a file back. If it's not, in this case, you just panic. And this is actually pretty nice, especially for working with libraries like HDF5, where everything and anything can cause an error, or can cause multiple errors and multiple threads at any point in time. And there's examples where traversing the error stack when trying to recover the error will cause more errors, and so it may get pretty hairy. So in Rust, when you have multiple procedures that can cause errors, you would have to match like every single one. So yeah, like you open a file, then it may fail or not. If it fails and you want to return immediately, there's nothing to do. You don't get the file handle back, then you want to read a string from a file, and this may fail or not, etc. And there's this is a verbose way of doing that, but there's also syntax that lets you just put question marks and a question mark is basically if it fails, return immediately and bundle an error back. And if it doesn't fail, you get whatever's inside that result. Okay, so this really helps a lot. Why I think it's a better model than exceptions. With exceptions, like both in C++ and in Python, you never really know what may throw an exception. You have to read all of the source code, like all of the downstream source code. So you kind of have to, if you're dealing with library you're not really familiar with, you kind of have to try catch just in case. And with dealing with C error codes is even worse, obviously, because you just have to manually check that every single time. And finally, there's no OOP in Rust. Instead, there's traits. They're basically like pure interfaces without that can do things, but they don't own the data. So the data may only be contained in enums or structs. And there's one rule. So basically, to implement a trait to like link an interface to a type, you either have to own the trait, so which means you've just written it yourself, it's in your library, or you have to own the type. So you can't implement a foreign trait for a foreign type because you'll start breaking stuff, obviously, which is nice because in Python you can, and in a way, so you can do whatever you want. You can just replace the built-ins and like have fun with that. So for example, you want to implement a trait that can square things, like for example, like for number, you want it to be able to square itself and return square, right? So we implemented for unsigned 32-bit integer, which is simply we're saying, okay, implement a trait, and here's an implementation. And now number 3 gains a method called .square, which is pretty nice. So you print that returns 9. So it's kind of like a revert. It's like an inverse way of doing OOP, right? And it's actually pretty powerful. So let's say we, like if we were to write this implementation for other integer types, it would look exactly the same. So it'll be literally copy and paste. So we can just say, okay, let's implement this trait for any number that can multiply itself by itself and return the same type back. So you write like 4 lines of code, and basically now every type that can multiply itself by itself gains the square method. This may also include other types if some other author of some other crates implemented multiplication for some crazy complex number type. Now those complex numbers know how to square themselves, so which is pretty nice. Which is something you wouldn't gain with a typical tree-like inheritance-based approach. You can also do crazy things like well, actually, this is fairly normal Rust. I don't expect you to understand all this, but the idea is there's traits like iterator. So for common syntax, like all the comparison operators, plus, minus, for loops, like for something, in something, there's traits for all of that, for all the syntax. So to loop over something, that something has to implement the iterator trait. So here we're saying we want to implement a .squared method on an iterator so that we get a new stream, a new iterator where all the values are squared. Okay, and we do that basically by doing something like this. So if a type implements our square trait, which we just implemented a few slides back, then for all iterators that over those items that know how to square themselves, which are those that know how to multiply themselves by themselves, we just implement this next method, which is the only method in the iterator trait. And what we gain is, so in the bottom, we can now loop over something saying, okay, 1 to infinity, take 4 numbers, dot squared, this prints like 1, 4, 9, 16. So that's kind of the way you build things in Rust, like block by block. So there's built-in traits for everything, like all the arithmetic operators, equalities, comparison. There's traits for debugging. If you want to print something, it has to implement those, like display and debug. Iterators, dereferences. There's a trait which is called copy, which changes the move semantics to copy semantics, but it's like a bitwise copy basically. And finally, you can also derive traits, which is extremely powerful. So if you have a struct with a bunch of fields, and each of them knows how to compare knows how to compare themselves to values of the same type by equality, you can say, okay, please implement this trait for me, which will require that all of those fields implement this trait as well. Okay, and so you, for example, in this case, 32-bit integer and bool know how to print themselves, so your struct now can be printed, which is very nice, because in C++ you have to write those things like over and over just in order to print them. And so finally, the compiler has an awesome, I think, error messages, like in general. So it tries to figure what went wrong and what you were trying to do. That's just a simple example where it says it expected like reference, found an integer, and consider like doing this, and that, which really helps if you're just learning Rust. So let's talk about the library itself. So this is the GitHub repo. Basically, if you just Google HDF5 Rust, this will be the first link. I've been hacking on that for the last few years, more or less. So the goal is to the end goal is to have like some high-level memory safe and thread safe interface to HDF5, kind of sort of close to the high-level part of H5Py. Also build system for multiple platforms, multiple versions within the same code base. Rust bindings to cover the entirety of HDF5 CAPI for multiple versions. Then bitwise equivalents for special types like variable length Unicode strings and variable length arrays and stuff like that. And finally, automatic data type generation for structs and enums using those procedural macros, so that you won't have to implement those yourself. This is somewhat close to an example I've shown in the morning for C++, but that was just really hash-defined hackery with text expansion, but here it's a lot more powerful. So like the first 4 points are pretty much done completely, and I think that's the most of the low-level work. And so I'm currently working on the high-level part of it, which requires just more thinking about the design. So about the build system, it builds on Linux, macOS, Windows with like a single command. We do run tests like CI test on all the platforms. It's tested against various versions of HDF5 from 1.8.4, I think, to the most recent one on multiple platforms like Fedora, Arch Linux, with Conda installed HDF5, with system installed HDF5. It tries its best to find the HDF5 library through like package config, homebrew, Conda, etc. You can also provide it with custom applications for the library. It tries to parse the pubconf headers to extract the flags with which the library was built to like enable, disable certain things. And all those flags are available at compile time. So this library consists of 4 crates, so like libraries in Rust terminology. So first there's a separate crate with CAPI bindings, which can be used separately from the rest. Then there's the types part with type descriptors and all those special types. Then there's a derive crate with that allows you to automatically derive HDF5 descriptors for types. And then there's the main high-level crate that depends on all of those. So just a few examples. That's how the CAPI looks like. These were mostly generated initially, and then some of them were corrected. So you would see equivalents of these in C headers and in like H5F public and stuff like that. So all of those have the same memory layout and alignment as the C structs, and enums are like of the same size. So you can easily convert convert those through just like pointed referencing, basically. Now, another goal was to support multiple versions of HDF5 within the same code base, which is easier in dynamic languages like Python, for example, where you can just do like if this, do that. But in static languages, some symbols may not exist, so things may not compile. So it takes a bit more work, especially when there's been a bunch of hassle in 1.10 release with I don't remember which symbol was this version 1, and then there's version 2, and then there was a macro that swapped between them, and then something went wrong, and then they were swapped back. So in cases like this is a bit of hassle to maintain within a single source, but it is possible nevertheless. So this is an example where this like CFG is kind of like an if-def in C++, where you can enable or disable certain parts of code based on in this case, based on the HDF5 version. There's also opt-in features. So when building the crate, you may say, I want MPIO enabled through like OpenAPI, for example. And then this will bring in a few more dependencies, like there's Rust bindings for that. And there's also a few work in progress features like LZF and BLOS compressors. So if you enable those, you will compile the sources using your system C compiler and CMake, and like statically link them in. So there's a few quirks with how HDF5 library works. For example, a really nasty part is the globals and library initialization. So some IDs are not static, and you can only get them when the library is initialized, right? And so like in HDF5 source, you can find things like this kind of defines. It looks like H5P root, but it's actually a macro that calls the H5 open every time and then returns you this static variable. And internal to library do not use that's the comment above. But there's no other way to actually get it from externally through the FFI. There's some pain points, like in Windows in the Visual Studio stack, the symbol is called __ imp something G. With GCC, it's called like IDG, so you can have to go through all of those like details to link it properly. But again, it works. In Rust, it looks like you get something that looks like a pointer, and if you dereference it, it will basically do the same thing what C library does. So you will initialize the library if it hasn't been initialized, and then return you the identifier. So that's the C API. So basically, it covers at this point, it covers the entirety of the C API, all of the structs, enums, functions, and callbacks, all of that, from 1.8.4 to basically to 1.10.5. So then there's the higher level API. The main goals are for it to be thread safe and memory safe. Another separate part is error handling. It has to be reasonably easy to use, as in fairly close to H5Type, maybe, which people are used to. Object hierarchy. Now there's no inheritance, there's no OP in Rust, so you can have to do it all backwards. So for example, all of the methods that exists for group type need to also exist to also work for file type, for example. And then there's location type, like both file and group are locations, and location is an object type, right? And finally, immutability by default. That's kind of a standard for Rust libraries. A good example would be property lists. For example, I don't know a single case. Well, I haven't seen a single case where you would want to modify a property list, like a file creation property list after you've created the file. That just doesn't make much sense. But in HDF5 you can do that because everything is mutable by default. So it's a bit safer to prevent doing that. and you can so in this API you can query, you can get the property list back, but you can't change it. So you can either create a new one, or you can copy it and change things, but it's frozen and locked when you get it back. And okay, so thread safety, so somewhat similar to H5Py. We need to provide thread safety without this like enable thread safe flag for library. So critical operations locked behind a recursive like reentrant mutex. So basically anything that can modify their stack has to be behind a mutex. The mutex system used is a parking lot, which is like new, one of the most performant mutexes around, that's used in Firefox these days. And we have to keep a thread safe global registry of object IDs to track because things may get invalidated in different threads, and you kind of have to have a hash map behind a mutex, and this hash map maps IDs to mutexes of reference counted mutexes or something like this, which basically ensures that you can safely clone IDs or like ID objects, and they get properly dropped and invalidated. This took a while to make it work. In Rust, by default, all the tests run in parallel in multiple threads. So the first time I've had more than one test, everything started to fail. And this is a good thing because they run in non-deterministic order. So this took like a good while to actually to make it work. Now error handling. So same as everywhere else in Rust, most HDF5 calls return HDF5 result, which captures stack on errors. So if something bad happens, it stops the world, locks the mutex, and tries to recover the stack if possible, and then batches it back in this like error message and this sort of error sum type. And there's also a possibility that something internal happened, like internal to the crate, not related to the library, like bad user input or something like this. And so as an example, like if you open a file in read mode, it will not return your file, it will return your result of a file. So you can have to unwrap that or do something with that. Now the object hierarchy, there's one trait which is called Deref, which is dereference in Rust, which is basically the star operator, so what happens on reference. And a nice thing about it is that the values, the like reference values are coerced automatically, and if one type dereferences to the other, then all the immutable methods from the child trait are implemented for the parent trait are implemented for the child trait, which basically makes all of the functions and methods that are implemented for the group, they're magically implemented for the file as well, which kind of builds this inheritance style hierarchy, but backwards. Okay. And another thing is if there's a method or a function that requires a group and then does something with it, you can easily pass the file. So kind of the same way as in C++, but there's no runtime polymorphism. This is all like monomorphized. So every single type is known exactly like at compile time. Now for the types, so there's an interface for type descriptors. I think this covers the entirety of what's available in HDF5, and a few of these are not available in C++ API, and I'm not sure H5Py, the most recent H5Py covers all of the variable length options. But in order for this to work, so I had to implement the like bitwise equivalents of variable length arrays and variable length strings, like in Rust as well. It's like a safe versions of that you can just cast from like a void star from C, and they kind of work. So basically, there's the main trait is called like H5Type, which is a trait that it's like it has a static method that doesn't take any parameters, that returns a type descriptor for a type, right? So for example, for a 32-bit integer, it will return you a type descriptor integer of size 4. Okay, and so you can implement it for any types. You can say, okay, here's my enum, here's my compound type. So these are the special data types like fixed ASCII, fixed Unicode, variable length ASCII Unicode, variable length arrays. The fixed length arrays is a native Rust type. And all of those types behave like the normal Rust string types and array types. Now for deriving, it's actually possible to derive this H5 type trait automatically, so it's not really meant to be implemented manually. So the way this works is, as I've said, there's a mechanism in Rust called procedural macros, and when you do this derive H5 type, this macro will receive a syntax tree for the struct or enum, and then you can like walk through it and find all the types, and you can implement basically you can implement this trait. In this case, it will implement the trait for this like color enum, so we'll assign all those names and values for the struct. It will walk through all the fields and will implement those as well, and then it will find this like color, which is of type color, which is a custom enum that you've implemented. And the nice thing about it is that if you have another crate that depends on your crate, this will be all of the types that derive from H5 type. They will still derive from H5 type. So you can have types that encapsulate other types, and you can derive this H5 type for them as well. So here's an example. It's like from an altered example from README, basically. Like the way this works, you can notice there's a bunch of question marks at the end of pretty much every line. So everything that can fail, if there's a question mark, if it's okay, then it unwraps the value and gives you that. If it's not okay, then it instantly returns. So it's kind of like a throw. So you can create HDF5 file. You can say, okay, create a new data set with colors. You can give it a name, give it a shape, unwrap that. Then you can write like a slice to the data set, unwrap that. You can create a new group. You can create a new data set within a group. You can write a bunch of values. In this case, it's a two-dimensional array. For multi-dimensional arrays, this crate uses a library called mdarray, which is kind of which aims to be like a NumPy for Rust, but it's still in like a work in progress. But it provides a good interface for generic multi-dimensional arrays. The same way you can read from files, so you can. It's pretty simple, really. So it's like a few lines of code. So you can open an HDF5 file. You can read 1D, for example, array, or you can read it then into raw vector stream. And so yeah, this basically asserts that you get back what you've written, and that's like the entire thing. You don't have to set up any comp type things. Everything is like derived automatically, so it like just works. Speed-wise, it will be pretty much the same as the C++ API. And so finally, so what already works, and things actually before I go here. So if we go to the GitHub page, see this, yep. So there's a link to the documentation, and some things are finished, some things are not, but I just want to give an example. So for example, of the, I don't know, like a file create property list, that's just like one of the multiple types of property lists. So you have a bunch of, so pretty much like every single thing you can do with this property list. You can see that it dereferences to the property list type. You can see that all the enums and structs have been mapped to their like Rust counterparts. So you can like click on each one and see that this is this and this is that. You have some enums, so like file space strategies. Again, these are enums that are counterparts to their like CAPI versions, but like encoded slightly differently. So I'm sorry, how do I get back? Yeah, so what's there's a bunch of things that I've implemented over the summer, but it hasn't been merged in yet. So there's LZF integration, which uses the sources that are available in H5Py. There's BLOSC integration, so it uses CMake to build BLOSC and statically link it in. There's LZF and BLOSC filters rewritten in pure Rust. There's like full filter pipeline rewritten to accommodate for that. There's a few more things like selections rewrite to accommodate for unlimited selections for virtual datasets, and like a full rewrite of the dataset API using like DCPL, DAPL property lists. So this will hopefully be merged in like within the next month, and then what's left? Well, it's quite a bit. There's like attribute support. There's like various things. Like HDF5 is a pretty big library. That's one thing I realized while doing this. But I would say like most of the heavy lifting, like super low level stuff is done. Just requires a bit of effort. Maybe some community help to finish this. And in the recent years, the Rust scientific community has been growing like super fast, and I've been getting requests from various folks and like working in various universities trying to integrate Rust in their scientific work. So who knows? Anyway, thank you.
Questions? Could you confirm there was a video that was advertised recently by one of the senior engineers at Intel saying Rust is the new C for Intel? Is this something that's we're going to have to learn in the future?
Maybe. So Rust is currently used in, well, Rust is sponsored by Mozilla. It's used in their new rendering engine, which is called Gecko for Firefox as a backend. It will probably be used in OpenDNS, so they're looking to rewrite the whole thing in Rust. A few weeks back, there was a message on Linux forums, LWN, saying that they will probably start accepting low-level drivers written in Rust. So it's slowly going there, I think, but it requires a bit of convincing, and it takes a bit of effort to learn.
If you watch your space, this is very interesting. Okay, if you know the question, no questions now? It's time to speak again.